Greetings, nerds. I'm going to be getting an RFID NFC injectable implant in my hand that I purchased from a company called Dangerous Things. And finally, I'm going to sit down with Amal Graafstra, the founder of Dangerous Things, and discuss what goes into making these devices and what his plans are for the future. Joining me today is founder of Dangerous Things and biohacker extraordinaire, Amal Graafstra. Amal, thanks for coming on, man.
Yeah, no problem.
First of all, I just want to start by saying I've had my next implant for just over a week now, and I am having a blast with it. I love it. This thing is fantastic. First thing I did was clone my work ID, so I'm like flashing my hand in front of the door to get in, and then I've got all sorts of other things planned for the high frequency. But it's been a lot of fun, man. I really enjoy it.
Yeah, that's awesome. You get that sense of magic when you kind of like
Yeah.
imagine, I can say after 16-ish years, it doesn't go away, that sense.
So, from what I understand, reading about you and your company and all of that, you got into biohacking in early to mid 2000s, and then you started Dangerous Things in 2013 out of your garage. So, my first question is, what made you take that leap from I'm going to stick stuff inside myself to I'm going to sell people stuff that they can stick in them?
Sure. Well, I guess like the kind of entrepreneurial spirit has always been kind of in the family. Like my grandparents started a dairy farm, and my dad started a couple of businesses. I was in IT consulting and kind of doing my own thing. So the leap to being a business wasn't that big of a leap, but the things that definitely forced me in that direction were, as you said, I put this in 2005, this one here in my left hand. It's been there for a long time now, but, that generated some buzz. And then in 2007, I wrote the RFID Toys book, which is a little bit ahead of its time, I think, because hobbyist electronics didn't really come back around into fashion until 2010, and by 2013, there's a lot of people doing hobbyist electronics and wanting to integrate RFID technology into those projects. And, they're finding what I had done, but there was no resource. There was no, like, where do you get this stuff and how do you put it in? So people were like sourcing it from just terrible places. And like, a lot of car keys, in fact, will have these kind of glass tube, transponders inside for security. And then we're, like taking that apart and trying to use those things. I'm like, no, it's terrible. So I was getting a lot of email, and I was seeing things happening that were just not good and safe. So I said, well, I can just ignore all these emails and just ignore this and try to do my own thing, or I can try to wrap a business around it and see where it goes, right? So yeah, I decided, let's launch Dangerous Things. I bought the domain off somebody who had it registered, and the first of the two goals was to make sure the things that we sold were tested and safe, right? So we sourced a bunch of stuff at first, and a lot of it didn't pass, right? This is the problem. Is that you buy stuff, off of what, like Alibaba of the day, and it just didn't. It was either there was contaminants in the glass, or the glass was not structurally correct. It was high tension points. It would break, it would shatter. Some of it was very thin, so that it wouldn't even sustain like an autoclave process. It would just crack and shatter. The resins inside used to secure the stuff was not safe. It was cytotoxic, that kind of stuff. So it was really kind of a shocker to me that like people were just buying the stuff and like kind of trying to ram it in their body. So we've sourced a lot from a lot of different suppliers and stuff, and found a few that were passed our test. And then very quickly we said, well, we also want to increase capability, so we'll crowdfund the first NFC compliant implantable transponder. And to do that, we'll want to source our own materials. So do our own materials management, and then have a contract factory assemble it rather than buy turnkey, right? And so that was a really big turning point for the materials and the product safety. And then the other goal was to make it safe for people to implant it. So I think the very first thing that I did, even before it was called Dangerous Things, like I set up like store.amal.net. It was just ridiculous. the first thing I did was I wrote a guide, like how to properly do this if you're going to do it. But I realized really, really quickly that was a bad idea. And then I said, well, how about we partner with piercers, like body piercers, because they're very familiar with skin. They're very familiar with needles. They practice aseptic procedure. They know how to not cross-contaminate things. Like that's such a big thing. And it's so difficult for a layman to pay attention to everything you touch, everything you breathe on, right? Like, and how to properly move sterile material, right? Like you lay out a field, and then when you pick up a thing to open and put on that field, the outside is contaminated. Your fingers are, and everything's contaminated. So when you open it, it has to open in a way that drops out without touching, right? Like just every nuance of keeping things sterile. Body piercers do that. It's second nature to them. So it just made sense. We started building a partner network and created a guide for professionals to follow on how to properly install these things. But yeah, that was like kind of the driving force, like being appalled at what was happening, but also just being inundated with requests. I was like, hey, let's just make it happen.
Very cool. Yeah, it's funny that you brought that up because like when I first started like learning about biohacking and looking into it, there were a few names, but probably just a handful of names of people that would always pop up. There was obviously you, then you have like Michael Laufer from Fourth East Vinegar, and then you have Left Antonym, who, well, let's just say she's reckless with some of the things that she has done in past years. But then, like I said, then there's you, who's kind of for lack of a better term, you're like the godfather of commercial biohacking. You tried to bring some sort of sense of legitimacy to a subculture that is really, by outside eyes, seen as really sketchy. So I thought that was pretty cool. So obviously, we're in the age of the pandemic right now. How has that affected the way that you do business or conduct it? Has it really affected you heavily?
A little bit, yeah, because like obviously customers can't bring those products into a lot of places. But to be honest, the what it did was it just shifted customers around. So there are definitely places that are that should be in lockdown but aren't, and they're operating with COVID best practices, but they're still operating. So it's only in a few places where piercers are actually closed for business, and then they kind of have these periods of, well, we're open for 2 weeks, so get all your stuff done, and then lockdown will happen again. So we're kind of going through these undulations. But in terms of business, we tend to say, okay, well, it's been rough and people can't really get things installed, so we'll run a sale or something and say buy it now, but just keep it on your shelf until you can get it installed, that kind of thing.
I've seen you. I mean, you have several implants. I actually did. Is that a new set of stitches I see there in your arm?
Yeah, it is. So actually, and here too.
Oh.
So and then one right here as well. So I just recently.
Okay.
Friday last. So it's been a week, but I had a bunch of stuff moved around. So this one was a prototype that was here in my arm it was only supposed to be 30 days, but it ended up being like 4 years. And so I just had that removed. And so checking that out, analyzing it, and probably eventually replacing with the next model, basically. And then here, so on my left second metacarpal here, my middle finger, I have a Flex NT, which is a very thin biopolymer thing. And so that's been working great. I could fist bump, readers. And even though I have an XNT here, glass tube in my hand, I wanted to be able to fist bump with either fist. So I put not a Flex tube, but it's like an experimental device. It's an NTAG 213 with a LED integrated in the inductor coil. And then there's some glow powder paint on it as well. So I can charge it up with a flashlight, and then it glows for a while. And it kicked around on my desk here for a while, and then I was like, well, I'm having this removed, so I might as well put that in here and have that done. And then this is like a needle installation of a prototype, another Vivoki prototype device.
So what's the most interesting or unique purpose you've found, either yourself or somebody else using one of these for?
Well, I think that's kind of interesting. So it's always going to be some sort of identity application for the most part. I think the most interesting customer application was somebody had put a digital tattoo on it. So if you scanned it, it would load up like an animated GIF from memory. There was also somebody who was giving away links to, they were like a game designer, so they were giving away links to a free copy of the game. Other people have put geocaching links on their implant, so to claim that geocache, you had to and like scan the implant to claim it. And then recently, we've been talking about NFTs, so non-fungible tokens, and being able to integrate that in some way so you generate a NFT when you scan the implants. But me personally, this prototype that came out was one of the early prototypes of the Vivoki, what's now called the Apex. It was 2 chip iterations prior to that, but anyway, I used it for PGP encryption, one-time password generation, all that kind of stuff. And that was like a daily driver. Like I used that almost every day, authenticating certain things. And it was so helpful too, because I don't know if you ever used like Google Authenticator or Microsoft Authenticator, you load the codes in it. Well, if you change phones, that is a real pain in the butt. And I've changed phones 3 times since I put it in, right? But I never had to bother with re-authenticating or re-tokenizing anything. I just put the reader app on and all my tokens are here and they're generated here. So it was a real like kind of eye-opener to, the idea of moving these critical identity things off of these phones, which are just kind of general computing devices, into a device that's literally within yourself. So all your kind of digital identity moves with you, no matter what device you might interact with. It's inside you. So let's say I didn't have my phone, or my phone battery was dead or whatever, but I needed to do some kind of data encryption or authentication. I could borrow anybody's phone, put the really simple app on, and then do what I need to do and hand the phone back. And there's no identity data or security data that moves back with that phone back into that person's hand. Like if you logged into Facebook on someone's phone and you didn't get a chance to log out, that's the deal, right? But for me, it'd be like I log in, I do my thing, and immediately hand them the phone. All the important stuff's here. It's not going with the phone. So that's a very important difference. The phone is no longer an identity analog for me. It is simply an interface.
I was actually going to bring up that a little bit later because when I first emailed you the very first time, I was trying to decide which implant I wanted to go with, and I was leaning between the Next or the Vivoki Spark. Because the idea of that biocryptography just really caught me. But the one thing I was a little concerned with there is it did look like that platform is still a little bit in its infantile stages. And I know you've kind of talked in the past about trying to get that up off the ground. So what's that process like, and what can we expect to see in those devices, and what's available now?
Sure, yeah. So Vivoki was launched in 2018, and at the time the goal was to create a platform that worked with the Spark and a series of services. And the Apex, which interacts with that platform, is part of it. But the interesting thing about the Apex that is due to be released this month or maybe early next month, it also can run autonomous applications that you load into the chip, right? So that's where the autonomy of that's where the OTP authenticator codes go. That's where the PGP encryption comes from. The chip itself, the Apex chip, is able to generate its own crypto keys on chip, meaning like you don't push keys into it. It can generate its own key pairs for public-private keys, meaning we don't have those keys, right? Like the chip itself is the authentication mechanism, and the platform becomes like the pipeline for moving commands and data around. But in terms of services, particularly with the Spark 2, because the Spark 2 doesn't have that autonomous code running capability, the plan was always to create services, as you said, and it is still in its infancy. But this year, 2021, we have a new set of co-founders that have joined the team. So we have now a well-defined, timeline for developing those types of things and deploying them. And I think the first thing we're going to be deploying soon is going to be either the computer login service with Vivoki Desktop Reader, or or the Vivoki Vault service. They're both being worked on kind of in parallel right now. I'm just not sure which one's going to get finished first. But the Vivoki Vault service would be similar to like One Login or Dashlane or LastPass, that kind of password management. But instead of a master password, there's the chip. So when you load the client and you want to authenticate, you scan your chip, and then that opens the vault. And the vault can store passwords and things, but also we're exploring things like secure file storage, secure images. So like you take a picture of your insurance card or credit card or loyalty card or whatever, you store those things in the vault as well. So those things are in the immediate, to be developed immediately kind of status.
So with the manufacturing process, I know you kind of talked about it earlier that you kind of outsource some of it. So how much of it are you actually doing in-house?
Yeah, so the anything that is injectable, so the glass form factor, the X series for dangerous things, and the Spark 2, for example, all that stuff that goes into syringes and then EO gas sterilization, that's done with a contract assembly factory. So we manage those materials, we source materials for construction, like the glass and the bioresins, that kind of stuff. And then the factory is contracted to assemble those things and then run it through EO processing. So they put the chip on the antenna, they put the resin in, they put it in there, seal it, put that glass transponder into the syringe, into the pouch, through EO gas sterilization, and then they ship to us for kitting. So we finalize the making of the kits here and everything. When it comes to flex devices, that's all artisan. So I make those here by hand, every one of those. And that's because at the moment, the flex, to make a flex device in a factory environment would require enough volume to set up a line to do that, a factory. And that's just not where we're at yet. So when when there's a process that needs to be done for making the flex, it's pretty much, a lot of it has been automated. So through partnerships with contract engineers, we've set up automation for that process, but it's still me who's the one who's like setting the electronics into the resins and getting it all processed and doing the finalization and pouching and all that stuff. That's me here.
Wow. Now with the flex transponders that you're using, that bioresin that's on there, you developed that all yourself, right?
Yeah, it was done in part with the chemistry house, basically. And so it was just through many iterations of trying to do things myself where I was like, finally I was like, I need to bring in some professional consultants here. And so we worked on that together and devised not just the material, but also the process. And yeah, then I just implemented it here with machines and it all works. So
all right. So obviously when you're trying to come up with a new tech for something like this, one of the biggest hurdles is size. But aside from that, what are some of the other difficulties that you come across when trying to bring out a new device?
Yeah, there's a couple things. First of all, the difficulties, for example, like with the Vivoki prototype that was on my arm and it went through the Flex 1 iteration and then to Vivoki Apex, there's a couple things there. One is volumes. So, for example, if I need a silicon die of a particular commercial chip, you basically, that just means the silicon wafer that's created and all the lithography has a bunch of die chips on it and they dice it up into these little chips. If I need the die size form factor for putting into glass, for example, that chip better be very popular, because if it's not very popular and you need to buy those from, you can buy them sometimes from vendors like third parties who buy full wafers of these things and then make devices and products. You buy a partial, right? So you buy some of those from them, then you can make your product. But if it's not all that popular or common, then you end up having a budget for it and buy a whole wafer. And sometimes that's just not possible. So let's say a 12-inch wafer is how these things are made, and the 12-inch wafer has 200,000 of these die chips on them, and the price of a chip a die chip is like $2. Well, guess how much a wafer costs? It's like 200K, right? So it
Yeah.
becomes very prohibitive to try to make some of these things. So you really have to, when you're dealing with low volume, and anything that biohacker company is going to be dealing with is going to be low volume in comparison. Like a single bank might ship out a million cards, right? A million chips a year or more, right? Whereas we're like, yeah, we need like a few thousand of this chip for this year. And they're like, yeah, we're not doing that, right? So just dealing with volume is a really, really difficult thing, and you have to be very good with partnering with suppliers and vendors to try to work deals and get the the tail ends of certain product runs from like maybe a card manufacturer. Say, hey, if you next time you buy a wafer, like set aside 1,000 of those die, and we'll buy them off you. We have to buy them at 3 times, 4 times the cost because it's a special order, and so that's a challenge. But the other side of the coin, or the other challenge rather, is just that when you're dealing with more advanced product and more capabilities and partnerships, you're bringing in more companies that you're partnering with to either facilitate those features or do integrations. Then you're dealing with aligning with partners, right? So all my ducks are in a row, but the partner's not ready, or they have their own hurdles, and they have to get they're ready with this, but then, oh shoot, now I need to get this other partner aligned so that I can connect these two things. And so just dealing with getting everything correctly situated when you're dealing with like multiple partners integrations, that's also a very big pain. But yeah, I mean, slowly we've been working toward this goal of getting, for example, the Vivoki Apex launched, and now we're like so close, but we don't want to rush. We don't want to rush it. So I keep having to like, it's coming. It's going to be next month, but it's almost there, and then we'll have a delay because I mean, one of the things we didn't count on or forgot about was Chinese New Year. So we had this plan to do this new inductor design, and then our vendor was like, "Oh yeah, we're going on vacation for like a month and a half." I'm like, "No." So these things come up like all the time. Anybody who's in manufacturing would know. Obviously, Chinese New Year factors in a lot of different products. Like even if we don't make the product there, the components come from there, right? So like, certain components, like I could get flex PCBs ordered anywhere, but even if I order them from the U.S., they have a factory in China that's producing them. Like it's just it's just where those things are done. So so it does affect things, even though you kind of forget about it.
You were just talking about the Vivoki Apex, which obviously sounds like a pretty cool project, but you've got a couple other things here that I kind of wanted to mention. One of them is more just looks like a little one-off kind of a deal, but I saw the video, and I think it was a custom job that you did where the girl installed a Disney Magic key in her wrist. Now, what's that process like? I mean, I imagine like some of those chips, I haven't pulled apart anything like for the Disney one, but is it a pretty delicate process to extract that out and then make it into an implantable object?
Sometimes, but to be honest, like the Disney Magic Band, it went through a couple iterations, and the latest iteration is a puck design. So it's like a little nugget, and then you can put that nugget into different wristbands, and it kind of becomes a style item, right? So that design, basically, I just cracked that open, and then inside there's a PCB and a bunch of components, and there's 2 parts to it. One is a Bluetooth low energy transponder that basically pings out an advertisement. It has a battery and all that. But separate to that, on the same PCB but totally separate, is a passive transponder. And that passive transponder is the thing that's used when you tap the Magic Band against the little Mickey reader, right? So I looked at that and I said, okay, well, there's the chip. Pulled it off, desoldered it from the board and pulled it off and tested it. And it happened to be a Desfire EV1, which is, we make the Flex DF with Desfire EV1s already. So I was like, yeah, I can turn this into an implant, right? So took the chip itself, cleaned it up, put it in through the process, put our antenna on it, our custom antenna, polymerized it, and then shipped it to her. And then it was just that simple. So all the electronics, the majority of the Magic Band, to be honest, is there to provide tracking information. So
Yeah.
as you walk in the park, it's transmitting advertisements, and there's beacons, beacons out your position basically, as calculated by the receivers in the park. And for an adult, that's not really all that useful for the adult. It's useful for Disney, but it's not really useful for the adult. But when you're thinking about putting a band on kids and letting them run wild in the park, then it becomes more obvious. Oh, as a parent, I can go, where's my kid, right?
Yeah.
Oh,
Yeah.
here. So that's helpful, and it really works or matters within the confines of the park, right? Although the Magic Bands, I believe, are still sending telemetry, they're still advertising beacons while not in the park. They're just advertising all the time. But I don't think it's a necessarily a privacy risk. There's so many things to do that already, like your phone and everything. And if you were concerned, you just wrap it in a couple sheets of tinfoil, and there you go. But anyway,
Yeah.
the point is that component that is used for access, right? Getting into the park and scanning your band at the shop to buy things, all those functions are part of the Deathfire EV1 passive transponder. So making an implant out of that seemed like a pretty no-brainer.
You partnered with and started releasing the Walletmore payment chip, which is very cool to me. Like that was again one of the things that if I can replace my wallet and my keys, we're good to go.
Yep.
But I did see currently that's only available in the EU, which is, sucks, but I understand it. You got to go through a lot of agencies and whatnot. Do you have anything in the works where you're trying to get payment available stateside, or?
Yeah, so essentially, Walletmore and partnering with them is a great step forward because their primary interest is payment implants. And Vivoki has always been interested in payment. It's been a feature that we've been pursuing. But the challenges that are presenting themselves are big. And so we decided, well, what we'll do then is we'll partner with Walletmore and we'll enable them with all of our kind of processing capabilities and manufacturing capabilities. We'll do that part of it. But they, Wojtek, who's the CEO, he gets to focus 100% of his effort and time on making a payment implant, right? And the goal is that eventually Walletmore will become a payment service on the Vivoki platform, right? When we're able to merge those kind of features and functions. So for us, it's very, very good that we have a partner that's dedicated to that one application, seeing a payment implant come to fruition. So at the moment, the only option really for U.S. payment is conversion. So there's a company called Pure Wrist. They have a token, like a little snap out card that you can put into a wearable, right? And so we take that chip out of the card and make a payment implant that looks very similar to the Walletmore and performs similarly, but it's US. And so at the moment, if you're in the EU, Walletmore is a good choice. If you're in the US, Pure Wrist is an option. There's other countries outside of both those regions. Some of them have devices that are available that can be converted, but all across the board, including Walletmore right now, there still happens to be an issue with expiration, right?
Mm-hmm.
So a Pure Wrist device will expire in 2 to 3 years. You have to replace it. Luckily, the size and shape and method of implanting a converted Pure Wrist means that replacement's not too difficult. It's a small incision either with a needle or a scalpel, and then you just slide out the old one, slide on the new one, Band-Aid, you're good to go. But the goal, of course, with Vivoki and Walletmore is that we have a fully tokenized, abstracted payment device. So works more like Apple Pay, where you link accounts to it in a way that when the account expires, you just get a new account or a new card or whatever and relink it. But the device itself doesn't need to be exchanged. So that is the goal. That is a possibility on a technical scale, on a technical level. It's really, at this point, just about working the relationships and getting the proper approvals from network operators like MasterCard and Visa.
Mm-hmm. That's interesting because I didn't realize that was, well, I mean, I think the one that you have now is closer to what's in the credit card, but you're saying the ultimate goal is something closer to the Apple Pay, correct?
Yeah, and in fact, Vivoki Apex will have that technical capability to operate as a tokenized payment device.
Okay.
It just comes down to, can we get those approvals and enable that functionality? So the functionality will be in the chip. It's just whether or not we can get it enabled and working on the payment network.
Interesting. Okay. I look forward to it, man. I'm excited for the day I can get one of those.
Yeah.
I feel like, NFC, RFID, it's a relatively old technology, but we've made some big steps in the last decade or so, and there's probably going to be a lot of little smaller ones along the way. But I feel like one of the biggest leaps that we're going to be able to make in terms of like a transhumanist kind of way is the ability to go from these passive chips like NFC and RFID to something that's more active. Now, obviously, there's a lot of hurdles there. You don't want to stick a lithium ion battery under somebody's skin or anything like that. But there are, I mean, I know there's been people that have looked into like thermoelectric conductors and things along those lines. Have you guys explored any of that avenue at all, or are you pretty much sticking with passive for the time being?
Yeah, absolutely. We looked into it. So just to clarify, like NFC, RFID, the thing that's important to remember about these technologies, even though they are old, is that they are a transport medium. So just like copper wire in a telephone line, right? It was just to transfer voice, but then we use that same wire to transfer data with modems, and then it got into DSL, and now we're doing cable, and so. But the copper wire is still the same copper wire. So when it comes to um, things like RFID or NFC, so many times people jump to the applications running across those transport mediums, but not those applications are just applications, right? So
Mhm.
yes, the applications can be new and very exciting and interesting, like contactless payment or whatever we're doing. But the bedrock of the transport mechanism is just simple,
Yeah.
passive magnetic field coupling, which is great because it's robust, right? That's why we use it, and the fact that it's um, the reader generating the energy for the transponder to do its work. That's also very useful for things like an implant, right? But transitioning to an active device would mean a lot. It would mean a huge change in applications, what we can do, data we can collect, ways that we can transmit that data, speeds at which we can transmit that data. Simple things like mass storage under the skin. I want a terabyte, that I
Hmm.
carry, whatever, Johnny Mnemonic, but I don't need to cut out a section of brain. I can just put it here, right? Like that kind of stuff is really, really intriguing. But as you said, like lithium ion battery chemistry is dangerous, right?
Yeah.
Off thermal runaways, fires, explosions, like hydrofluoric acid, which like would kill you immediately. So yeah, a lot of problems. And so I have a lot of conversations with people as to why that is a problem, and I'll just iterate it here shortly, briefly. Essentially, lithium ion or any battery chemistry really that you might see in a pacemaker or a medical device, the reason that it's safe enough for a medical device is that every component, every piece of PCB, every wire has been quality assurance checked and inspected. That is a very expensive process. So you have a battery that's made in a medical device factory to very exacting spec. Every production battery is inspected. Every component on the board is inspected. All the stuff is inspected. So the price goes to like for something that as a consumer product without all that scrutiny would maybe cost $20 to make. Now costs 20,000, right? Or it's just
Yeah.
crazy money to make. But that's why those things are expensive as heck. Um, but if you have a consumer grade device, right, you buy the cheap resistors, you've got a couple transistors, a few PCB maker makes a bunch. PCBs are not 100%. You can definitely get PCBs that have problems or defects inside of them. You can't see with the eye. You have to do X-ray inspection to find them. Pathways might not be complete, or pathways might be shorted, or pathways might be shorted in a way that it's intermittent, right? You
Hmm.
have a movement when it's short. So all of these things in consumer grade components are a problem because if you have the failure of the wrong component or a component just goes out of spec, it's still working, but it's not within spec, suddenly your battery is overcharging or your battery is over discharging or the current draw is above spec and the battery heats up and now you have chemical reactions that cause off-gassing, which in a hermetically sealed implant creates pressure inside and cracks it, and then you got liquids coming in and now it's mixing and boom, right? So um, as a consumer grade device, which is the point and the goal here, um, you don't want to buy a fun implant for $10,000. You want to buy it for $100 or
Yeah.
whatever. So this is the issue. And what we really need to find, and what we've been keeping our eye on, is new battery chemistries and manufacturing capabilities and techniques that enable high energy density. So you need to be able to pack a lot of power into a very small volume, and charge cycle counts. Like, you don't want to, you recharge a battery only so many times before it won't carry a charge. Chemically, it degrades, and now it doesn't work anymore. And so you need something that's very high energy density, very high charge cycle count, and essentially bulletproof. Like, you need to be able to shove a knife through it and have it not explode. You need to be able to connect the two ends together and short it completely and not have it explode, or off gas. I mean, it's not just about explosions. It has to literally not produce any chemistry outside the norm function. So it can't produce hydrogen gas. It can't leak anything. It needs to be able to be torn, ruptured, like destroyed, and have thermal runaway. So that's a very tall order. Right?
Yeah, absolutely.
So it's just, it is a huge problem, and it's a huge hurdle. And I don't know that we're going to see anything that miraculous coming down the pipe, except for one thing, which is there are all the same needs exist for electric cars, right? You don't want those exploding. You don't want them to cost $1 million. You don't want them to off gas. So they're kind of the same requirement. They need to withstand a car crash that rips them in half and not explode. Like, so there's all these kind of similar things. The challenge will be to ensure that those manufacturing techniques used to make those giant batteries can be downsized to make tiny little ones for implants. That would make all the difference. And so we're keeping our eye on it, and we're very excited for those things to become a reality, because, man, once that exists, you're going to see some crazy stuff coming.
Oh, absolutely. Yeah, I feel like, I keep on hearing Elon Musk and Tesla, they're looking a lot into like the solid state batteries and whatnot. And yeah, it'll be a game changer for sure. Did you see the thing that I think it was a recent article that came out? Some research institution has come up with, I mean, this is more in terms of wearable tech rather than, implants or anything, but they have some sort of biopolymer that they're working with, or I'm sorry, thermoelectric conductive polymer that they're working with that will charge electronics. Now, with that though, I feel like it's a matter of always having enough current and voltage to constantly power this device, rather than like a solar panel. It's not going to work at night. You got to find something that's going to have a steady stream of power, but also still be enough to power whatever it is that you're doing with it. And I feel like that's probably a challenge, but do you have any insight on that at all?
Sure, yeah. So when it comes to TEG or thermoelectric generation or any of these things, what we're talking about is energy harvesting, right? So we're harvesting either RF energy, kinetic energy, thermal energy, but we're harvesting it, and it's a very low amount, right? And so when we're talking about charging electronics or whatever, you're back to needing to store that power into a battery, right? So then it's the same problem. But as you said, if we can generate enough power either consistently or just during the times that we need it, then there's a couple options. One, we could directly power the electronics, which requires a lot, right? There's peak draw when you're transmitting a radio packet, for example. Your peak draw goes way up. You turn the LED on, your peak power goes way up. So you need to be able to cover all of those deficits, right? All those needs, which is very difficult to do usually, particularly with energy harvesting. The consistency of energy harvesting is also pretty bad. Like, there are changes all the time happening, so you're not always moving your, a kinetic watch, right? You're not always moving your wrist. You're not always, generating the same amount of energy delta from the surrounding environment. Like, what if it's a hot day, right? Then you're not. So, but ultimately, the bottom line is that those kinds of things, outside of something, say, like, let's say they figure out glucose fuel cells, right? That would be like the ultimate. If you had a glucose fuel cell that was resilient, reliable, robust, kept working for decades, or at least a decade, right? And it was small, then you'd have your power, right? Glucose is one of the most energetic molecules. That's why we use it for energy. But Outside of that, with the more typical energy harvesting and type of things, you mentioned solar panels. I did put a solar panel under my skin to test
Really
to make sure that it was a possibility, at least on low melanin skin, white skin, and it did work. I mean, it showed promise. So,
interesting.
but the problem again is like consistency. So specifically though, for thermoelectric generation, I want to mention that when you see these kind of things, like there was a watch that came out that was like, oh, we can power ourselves off your body heat, right? The thing about that is your body does a really good job of thermal regulation, right? So when you have heat loss through an area, your blood vessels will constrict unless you're trying to get rid of heat, right? If you've been working out, you got a lot of excess heat, your body's going to try to get rid of it. All your blood vessels on your skin will open up. You try to get rid of all that heat. But if you have something that's drawing heat out, or you're losing heat through an area, those blood vessels naturally constrict to slow heat loss, right? So your body
Yeah.
will fight back against that kind of thing. And the delta, the difference between the ambient temperature and your body temperature, particularly on the extremities, is not all that huge.
Yeah.
It's not typically all that much different. So you need a lot of surface area to gather enough electrons as well. So you need to have this really big area of like the entire back of a watch face to power something that a watch battery can power for many years, right?
Yeah.
So your energy requirements for a typical watch that's like got a quartz crystal and like an LCD display is extremely, extremely low. And so compare that to a Bluetooth device, right? You're radio transmitting, you got LEDs maybe for an interface or whatever. The power requirements of such a device are orders of magnitude higher than a watch or a pacemaker for that matter. Pacemaker is an extremely low power, purpose-built microcontroller device. They've made the silicon die do exactly what it needs to do, and no extra power is wasted. It's not a general computing CPU. It's doing exactly what it needs to do for the lowest power budget. And then the amount of actual power in terms of voltage and amperage required to stimulate neurons in your heart is like micro. It's so tiny, the amount of energy actually needed to do that when you have an electrode positioned right on the heart muscle, that a battery that's super tiny can run for 10 years no problem. So it's again, when we're talking about power requirements for the application, typically biohackers are interested in stuff like doing sensing of biomaterial, bio data, transmitting that data out. Like all those kinds of things require massive amounts of power in comparison to like a watch or a pacemaker. So your power budgets become insane. And when you want to explore this possibility, there's just no way that an energy harvesting mechanism would be able to power those things directly. So you're back to having to store power somehow. And people have talked about ultracapacitors or super ultracapacitors or that type of technology over a battery, right? Because you can have infinite charge cycles. It's not going to break down, or at least not very quickly. And so the problem with those technologies is energy density is very, very low. So you have the energy capacity of a capacitor per volume. You might have something like that big, right, as a supercapacitor, to have the same kind of energy density of a battery that's like a tenth that, right?
Mm-hmm.
So, or less, far less actually. So you have these multiple problems of energy density, charge cycle, safety, like all these things working against you for these active electronic implants that are, again, consumer grade. So that's probably the biggest thing, between, it's not just QA and all the costs of a medical device versus a consumer grade device. It's also the application. Like if you look at a pacemaker or a deep brain stimulator, for example, those devices are all battery powered, but their power requirements are so extremely low that they don't need to worry so much about battery capacity. And they can put a lot of extra manufacturing materials, safety, all that stuff into these devices and batteries and make it work.
I'll let you go here in just a second, but before I do, I just wanted to ask, is there, you mentioned the Apex coming out and whatnot, but are there any other techs or products or anything that you have in the pipeline that you can tell us about or want to tell us about, or?
There are things in the pipeline that are super exciting, but really can't talk about them at all.
Yeah, I totally get that. Okay. All right. Well, Amal, I really, again, like I said, I really appreciate you sitting down, and this has been enlightening to say the least. And enjoy your day, man.
Yeah, man. Thanks. We'll talk
Yeah.
soon, I'm sure.
Yeah. I appreciate it. I'll be in touch.